Ask my instructor 15.4.33. The question is stated this way. Use Green's theorem to evaluate the following line integral. Assume the curve is oriented counterclockwise. The circulation line integral of f, where C is the boundary of the region R. First of all, I'd like to get a handle on what that question just said. This is the way that I view the question. We're going to use Green's theorem to find the components of f that are in the direction of the curve C, where C is oriented in a counterclockwise direction around the following region. Recall that we can use a parameterization of C to find circulation. However, if we wish to avoid doing a line integral, we can use a Green's theorem instead. Thanks to Green's theorem, we now have a manageable double integral. One side note I'd like to make is that Green's theorem assumes counterclockwise direction, and so when the problem told us that the curve was oriented in a counterclockwise direction, it was basically telling us that we could use Green's theorem. For this vector field, the curl is 9x squared minus 6xy, and the double integral is the double integral of not the curl, where y goes from 0 to sine x and x goes from 0 to pi. We first need to integrate with respect to y and evaluate. This is where the problem gets fairly interesting. What I did to do for this problem is I decided it was easiest for me to break this up into two integrals and to also use integration by parts for each integral. So this is the integral broken up into two integrals. And I'm going to, in this little video lecture, I'm going to break the lecture up into two parts. One is for the first integral, and the second part will be for the second integral. So first let's tackle x squared sine x using integration by parts. If u equals x squared, then du equals 2x dx. If dv equals sine x, then v equals negative cosine x. X squared cosine x, the negative of that evaluated from 0 to pi, is pi squared. We next need to look at the integral of 2x cosine x, and we need to use integration by parts on that. When we do integration by parts, the uv equals 2x sine x, and the duv equals twice of sine x dx. Sine x evaluated both at pi and at 0 is equal to 0. And so this first evaluation, I just get 0 minus 0. Then sine x, the antiderivative of sine x, is negative cosine x, and my double negatives cancel. Then I just need to evaluate cosine x from 0 to pi. When the dust settles, I'm left with pi squared minus 4. Part 2. For this part, I recommend using the power-reducing formula. And then again, breaking it up into two integrals. The first integral is fairly straightforward. The second integral, I recommend using integration by parts. For the first integral, I get 1/4 pi squared. For the second integral, my uv, I get 1/4 x sine 2x. that I'm going to evaluate from 0 to pi. And for my duv, I get 1/4 sine 2x. Now sine 2x evaluated from 0 to pi is just 0 minus 0. And so it doesn't even matter that we have the 1/4 x. The integral of, the integral of sine 2x is just 1/2 cosine 2x, and then I just go 1/2 times 1/4 is an eighth. Now cosine 2x evaluated from 0 to pi is 1 minus 1. And so for that I get 0 as well. And when the dust settles, I have 1/4 pi squared. Let's put this all together. Don't forget to add in the coefficients of 9 and -3. When I do that and do the arithmetic, I'm left with 33/4 pi squared minus 36. Have a nice day.